All right, today I'm going to start the review on Chapter 15, Solutions, and this will be the material covered in Exam 6. In your schedule, the syllabus schedule says that today is a buffer day, but since we've already finished presenting the new material, I'm going to start the review today, and we'll probably finish it today. That means that this being Thursday, next Tuesday, which will be April. No, March 31st will be next Tuesday. March 31st will be a tutorial day. So I'll Zoom in from my office, and if any of you have trouble that you need to deal with, we can deal with it there one-on-one. So let's get started. I've got some that are highlighted, and I want to be sure and get to these. And number one, how many grams of calcium chloride, gives you the molar mass there, so you don't have to calculate it, are needed to prepare 5.17 liters of 0.5 molar calcium chloride solution. All right, so the concentration we're given as 0.5 molar solution. We also told that we want a final volume of 5.17 liters. Okay. And we want to know how many grams of calcium chloride. So we want to know the mass, calcium chloride mass. Right? We can't go directly there, right? Molarity is in terms of moles per liter. So one of our unknowns is also the number of moles. So we go back to the original formula. Molarity equals moles per unit volume, and we solve for moles. So moles equals molarity times volume. And we do have 0.5. What does molar mean? Molar means moles per liter. And then volume is 5.17 liters. So that way, liters cancel, leaves us with moles. So let's see, what's half of that? Let's see, half of 17 is 8. Carry the 1. That's what it was, 5. Is that it? 258? No, that's not it. There we go. 2.585 mole. Well, I kept an extra decimal point so that we can avoid rounding error. We'll round off to 3 decimal places at the end. All right, so now that we know how many moles, right? We want to convert to mass. Our conversion factor is grams per mole, which is molar mass. And we're given molar mass as 111. So all we have to do now is multiply that value, and we get 2.86935 times 10 to the second. And we're going to round off to 3 decimal places. And notice that the answers are given in standard notation. So we're going to round off to this position, 1, 2, 3, which makes that 7. And then times 10 squared equals 287 grams. Okay. Right, number 2. What mass of solute is contained in 64.9 milliliters of 2 molar sodium bromide? So 64.9 milliliters is given as our volume. Right? And the concentration is 2 molar. And the question is, what's the mass, right, of sodium bromide? So you know how to write that formula. Sodium, bromine, -1 + 1. That's it right there. And we want the mass. Well, we have the same problem as before. We can't go there until we know moles. Right? So molarity times volume equals moles. But we have another problem. Units of measure, the wrong units of measure for this calculation. So what we need is, what's that equal to in liters? So you know what? Let's do it down here. 64.9 milliliters. What does milli mean? Milli means 10 to the -3. So 10 to the -3, substituting for this one, right? 64.9 times that. So 64.9 times 10 to the -3 liters. And your calculator is perfectly fine with that. It doesn't have to be scientific notation to plug it into your calculator. So we can just go ahead and do this. Right? 2 moles per liter. Right? That's what this is. Times volume, 64.9 times 10 to the -3 liter equals so many moles. All right. And let's see, we're headed for standard notation, so I'm going to go ahead and give it to you in standard notation. 1, 2, 9, 8. And this is malt. Now, we want a conversion factor that will convert this to mass. Right? Numerator, denominator. It's not given to us this time. We have to calculate it. So sodium is 23 grams per mole. Bromine is 7990, 79.90. We just add those together because there's only one of each. And this is 102.90. So there is the molar mass, and that's times that value. And we get 13.35642 grams. But we can only keep 3. So we'll round it off to 13.4 grams. All right. Number 3. number 3. You have 3 liters of 3.65 molar sodium chloride aqueous solution and 2 liters of 2 molar silver nitrate. Mix these solutions together, making a new solution. Calculate the concentration in molarity of silver ions in solution C. Let's see. Okay, we do that. So what we have here is a double replacement with a precipitate, and I'll show you that. Sodium chloride and silver nitrate. So we've got sodium chloride and silver nitrate yields what? We just swap places, right? Silver chloride and sodium nitrate. Oops. Is that aqueous? Look it up in your solubility chart and find that this is a solid. And then sodium nitrate is still in solution. Okay. So are we balanced first? Well, 1 sodium, 1 chlorine, 1 sodium, 1 nitrate. We're already balanced. So let's put what we know up here. 3 liters of 3.67 molar. And 2 liters of 2 molar. Okay. All right, that's given. And the question is concentration of silver ions. Well, we got to decide, are there any silver ions left? Because we're going to use some of them in this solid. So what's left over in solution? We got to find out how many of them are used for that solid. Then we can calculate the concentration. So first off, we have to find out which one of these reactants is limiting. So remember, if molarity equals moles per unit volume, then moles equals molarity times volume. So if we multiply these two together, molarity times volume, we'll get the number of moles of that compound. All right, so let's do that first. We got 11.01 moles. And this is sodium chloride. All right. We do the same thing for this one. I'm going to do it down here so we can string our calculations across. This would be 4 moles of silver nitrate. Okay. So what we want to do is find out if all of this is used up, how much of that will we get? And same thing for this one. And the one that produces the smallest amount is the limiting one. Okay, so we got this one, and we're going to convert to silver chloride. Ratio is 1 to 1, right? That was easy. 11.01 moles of silver chloride. Okay, same thing for this one. This is silver nitrate, silver chloride. That's 1 to 1. So we get 4 moles of silver chloride. Oops. Silver chloride. Okay, so it's easy. We find out which one's limiting. It's this one right here. This is the limiting one. This one is used up. Right? This one's excess. So what does that mean? Well, if we're only going to calculate the concentration of silver ions, are there any silver ions left from here? No, we used them all up. So the concentration of silver ions in solution is 0. All right. Let's use the same reaction for number 6. Be different values, but the same reaction. And we might also get something different here. So let's remove that part and set the stage for number 6. Okay. Starting conditions. 3 liters of 3.48 molar. Okay. I'm going to go ahead and calculate that because you know we're going to need it. This is 1044. 10.44 moles of sodium chloride. And silver nitrate now is going to be the same, 2 liters of 2 molar. All right, so that's 4 moles of silver nitrate. I think it's pretty safe to say, since the conversion is 1-to-1, right? 1 here to 1 there, 1 here to 1 there, that this is going to be limiting again. And this is excess. Okay, what's the question? Calculate the concentration of sodium ions in solution. All right, where are the sodium ions? Well, they started out over here, didn't they? Sodium ions. Where are they on the other side? We have exactly the same number of moles of sodium on both sides. So if we have 10.44 moles of sodium chloride, we also have 10.44 moles of sodium ions. Right? 1-to-1. What changed? The volume changed. Instead of 3 liters now for this solution, we have 5 liters total. So 10.44, 5 gives us 2.09 molar sodium ions in solution. Okay. Now let's see, we've got let's go down to 47, I think. That one uses the same reaction, but the conditions may change. Conditions do change. So let's set it up like we did before. Let's do that. Move that. Here, 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 and here. And let's put in our new conditions. 3 liters of 3 molar sodium chloride. That'll give us 9 moles of sodium chloride. And silver nitrate is 2 liters of 1.84. And let's be consistent. 1.84 molar and 2 liters. Okay, so that's going to be, let's see, 816. Oops, not right. Is it? Say 2, 8, 16. Yeah, 3.68 mole of silver nitrate. Okay, so since they're 1-to-1, this is going to produce, if all of it is used, we would get 9 moles of silver chloride. If all of this is used, we get 3.68 moles. So again, silver nitrate is limiting. But what's the question? Calculate the concentration of nitrate ions in solution. All right, this is similar to our previous problem, only now we're interested in nitrate concentration. Well, the nitrate is a spectator, right? It doesn't participate in the precipitation. It's a spectator. So we have this many moles of silver nitrate. We also have this many moles of nitrate ions. In how much volume? 3 plus 2 is 5 again. So we have 3.68 and 5 divided. So this is 0.736 molar. Okay. Let's see. We got another one using the same reaction. Okay. Different conditions. So we're going to use the same reaction, but we're going to change the numbers. Again. All right. Okay. Let's clean that up. Clean this up. All right. 3 liters of 3.77 molar. 3.77 molar. 3 liters. Okay. And 2 and 2 again. Okay. This is going to give us another 4 moles of silver nitrate. And this is going to give us 11.31 moles of sodium chloride. Okay. So I think we can see again that silver nitrate is limiting. And this is excess. Okay. The question is, what's the concentration of chloride ions in solution? We have to find out how many of these chloride ions are used up in this process. If this is going to produce 4 moles of silver chloride, that means that we've used up in the reaction 4 moles of chloride ions. Right? How many did we start with? Well, 1 to 1, we started with 11.31 moles of chloride to start. So we used up 4 of them. That means we have how many left? We have 7.31 moles chloride remain. Okay? So what's the concentration? Well, we need a volume now, don't we? 3 liters plus 2 liters is 5. 5 liters. So we're dividing 5 into that. And we get, let's see, 3 significant figures. 1.46 molar chloride ions. Okay? Now we can go back up to the top and pick up where we left off. Okay. Number 4. Go back to number 4. Let's see. Okay, number 4. Molarity of chloride in 110 milliliters of solution containing 3.22 grams of calcium chloride. All right. The question, right? First thing you got to do is find out what's the question. The molarity of chloride. That's the question. Of chloride ions in this solution. Okay. What are we given? 110 milliliters of final volume. Okay. And 3.22 grams of calcium chloride. So the mass of calcium chloride equals 3.22 grams. Okay, that's everything we're given. In order to calculate this, we need moles of chloride ions, right? Moles of chloride ions. 3.22 grams of calcium chloride is how many moles of calcium chloride, right? So we need a conversion factor. Molar mass of calcium chloride. Calcium's 40.08. And 2 times chlorine. And that's 110.98. Well, they gave us that one earlier. They gave us 111 in the first problem. We're going to go with this one. 110.98. Okay, this is moles of calcium chloride. Right? We want chloride ions. So what's the ratio? For every one of those, you have 2 of these. Okay? So that will give us the moles of chloride ions. And I get 5.8028 times 10 to the minus 2 chloride ions. This is moles. Okay. So we want to know what's the molarity. Well, now that we have the moles, right? We have the moles, 5.8028 times 10 to the minus 2 chloride. Let's see. Get our units in here. Moles of chloride. Now we need volume. Volume has to be in liters. This is in milliliters. How many liters is 110 milliliters? Remember, if the units are going to get larger, small to large, then the number has to get large to small. So that means the decimal has to move to the left. How many places? Well, the ratio is 1,000 milliliters per liter. So that's 3 positions. That's how many liters we're dealing with. Now we can divide that by 0.11. And I get 0. I'm going to round it off to 3 decimal places. 528. 528 molar chloride ions. And there it is, C. All right. It's number 4. 5. What volume of 12 molar nitric acid is required to prepare 6.71 liters of 0.1 molar nitric acid? Okay, what type of problem is this? We have two concentrations there and one volume, which tells me this is a dilution problem. Okay, so remember, M concentrated, volume concentrated equals molarity dilute times volume dilute. So our units, our variables need some definition. What numbers go where? Which one's the concentrated concentration? 12 molar. What's the volume? We don't know. That's the question. What volume of 12 molar? What's the molarity of the dilute solution? 0.1 molar. And the volume of the dilute solution is 6.71 liters. Okay? All right, so now we have them in the proper position. We can plug them into the formula and get our answer. We want to solve for this one right here. So that would be VC equals M dilute, volume dilute divided by molarity, concentrated. All right. So here we have 0.1 molar and volume 6.71 liters and 12 molar. There we go. That's the thinking part. The only thinking we have to do now is get the calculator to work properly. 0.1, 6.71 times that and divided by 12 is, okay, we need, is this standard notation? Standard notation. I'm going to put it in the scientific first because that's how my calculator reports it. 10 to the minus 2. So in standard notation, that would move 2 places to the left. Liters. Okay. All right. So now we can go to, done 6 already. We can go down to number 9. Let's see. Yes, number 9. You have 3 ammonium sulfate solutions on a lab table in front of you. All of the solutions came from a 500 milliliter volumetric flask containing 3 molar ammonium sulfate. How many moles of ions does solution 2 contain? All right, we're starting off with 3 molar. What we've got here is extra information. The question is about solution 2, so we don't care about solution 1 or 3. Also, we have the concentration of 3 molar ammonium sulfate, and we're interested in 68.7 milliliters of that solution. The fact that it came from a 500 milliliter volumetric flask doesn't matter because now we already know the concentration. So the concentration of ammonium sulfate is 3 molar. Ammonium sulfate. Okay. Let's see. How many moles of ions does solution 2 contain? All right. if we want to find out how many moles of ions, we got to find out how many moles of that compound first. And we have to write the compound correctly, because in solution, that will produce 2 ammonias and 1 sulfate. All right. So if we have a volume of 68.7 milliliters, I have 2 choices here. I can go ahead and multiply this times that, and the outcome will be millimoles. But I still have to convert it to moles because the answers are in moles. So I'm going to go ahead and convert it to moles now, to liters. So this would be 68.7 times 10 to the minus 3, right? That thing right there, liters. And then I'm going to multiply 3 moles per liter, right? That's what this is right here. And multiply that times 68.7 times 10 to the minus 3 liters. And that gives me moles of compound. Right? This is ammonium sulfate. So what I want to do is convert to ions. So for every unit of ammonium sulfate, how many ions do I have? 2 plus 1 is 3. So we have 3 ions for each one. Now I can take 3 molar times 68.7 minus 3 times, and then 3 times. So we want to know, let's see, standard notation. All right, 0.618 mole of ions. Okay. Right. Number 9. Right. Number 10. This is a simple memory problem. Time to regurgitate an answer. A mixture of sand and water is, it's not a solution, right? Sand doesn't go into solution. There are no solutes and there are no solvents, because those are only reference solutions. So we have none of these is the answer, right? None of those. Sand and water is a heterogeneous mixture, right? But that's not one of your selections, right? So it's none of the above. How about 11? Right? A chemist needs 225 milliliters of 3.1 molar HCl, hydrochloric acid. What volume of 12 molar hydrochloric acid must be dissolved in water to form this solution? All right. That's a dilution problem again. So we're going to have molarity of concentrated, volume concentrated, molarity of dilute, volume of dilute. Which one are we looking for? Volume of 12 molar. Volume of the concentrated, right? That's 12 molar HCl. The dilute, we want 225 milliliters. Excuse me, down here. 225 milliliters at what concentration? 3.1 molar. Okay. And the answer is in milliliters. All right. So what we've what we've learned is that in this type of problem, it's a ratio. So the volume that you start with is the volume you end with. The units of measure are the ones you end with. So if we just keep that the way it is and say, let's see, VC equals MdVd over MC, then we have 12 molar and a volume, excuse me, that's not right. 12 goes in the bottom. There we go. This is 3.1 molar, and this is 225. See, this is molarity. Molarities cancel, leave us with milliliters. So our answer is going to be in the units of milliliters. And this is going to be 0.5812 milliliters. And the nearest one to that one is, wait a minute. Something went wrong. I punched the wrong numbers in, I bet. Yeah, I punched the wrong numbers in. Okay. Right numbers, wrong decimal place. 58.125. So 58, the closest one is E. All right, 13. You have 250 milliliters of 4 molar sugar solution. You add 376.3 milliliters of water to the solution. What's the concentration of sugar after you add? All right. This is definitely a dilution problem, but we have to determine the values that go in the positions. We're saying, what's the concentration of sugar after? That's the dilute concentration. So the molarity of the dilute is unknown. Volume of the dilute, it would be a value. Volume of the concentrated, molarity of the concentrated. So the concentrated solution is 4 molar. And the volume of the concentrated is 250 milliliters. All right. And the volume of the dilute is what? We added 376.3 milliliters to the original. So the final volume is actually 250 plus 376.3. That's the final volume. This is 626.3 milliliters. There we go. So now we can say MCVC equals MDVD and solve for MD. E. There we go. So concentrated molarity is 4. 250 milliliters. And the final volume is 626.3. Okay. So milliliters cancel, leaves us with molarity. Let's see, 4 and 250, and we divide. So I get, let's see, three significant figures. I get 1.60 molar. Okay. Now, this is a multiple choice question. And in a multiple choice question, you have various answers that are given. And some of those you can be pretty sure that whoever created that question worked the problem wrong one or two or maybe three times and got different answers. So that if you work the problem the same way wrong, you'll get an answer that's there, but it's the wrong answer. So you have to know what you're doing to get the right answer. All right, number 14. Let's see here. Go to a fresh marker. You have two hydrochloric acid solutions labeled A and B. Solution A has greater concentration than B. Which of the following statements is or are true? Okay. All right, let's reason this out. The molarity of A is greater than the molarity of B. Okay? So what does that mean? Moles per unit volume. Moles of A per volume of A is greater than moles of B per volume of B. Okay? So if we look at each one in turn, let's see. Yeah, we do have 5. There we go. And D says at least 2 of the above statements are true. Actually, that references A, B, C, and E. So we got to look at each of the others to be sure that we don't have 2 that are true. That would make D true. So A says if we have equal volumes of both solutions, if these are equal, right? Solution B must contain more moles than A. Well, if these are equal, the only way that this quotient can be bigger than that quotient is for A to be bigger than B. The statement says B is greater than A. That's false. All right. B says adding more moles of HCl to both solutions will make them less concentrated. You increase the numerator, you increase the quotient. So that one's false also. How about C? To obtain equal concentrations of both solutions, you must add a certain amount of water to solution B. What if you added more here? It makes the denominator bigger. It makes the quotient smaller. So the relationship is still bigger to smaller. It doesn't make this one equal to that one under any circumstances. And then let's skip down to E. If you have equal moles of HCl in both solutions, okay, solution B must have a greater volume. Yes, if these are equal, the only way that you can get this one to be smaller is to increase the denominator. The volume must be greater if these two values are equal. So that one is true. And that makes this one false also. So E is the only true statement of that group. All right. Who's next? 16. a 116.9 gram sample of nitric acid solution that is 70% by mass of HNO3 contains how many moles of nitric acid? So what are we given? 116.9 grams of solution. So the mass of the solution equals 116.9 grams. Okay, this is an aqueous solution. All right, and it's 70% nitric by mass. So the concentration of HNO3 equals 70% mass. Okay, we want to know how many moles of HNO3. Well, what do you need to know to get moles? Out of this information, it's all mass. So we're eventually going to have to say molar mass. We can find the mass here, but that doesn't give us the moles. So we need to find how much mass of HNO3 does this represent? And you have to look at this term. This is mass. So that means 70.0 grams of HNO3 per 100 grams of solution. That's what that means. Okay, if you have this many grams of solution and you multiply it by this value, then the grams of solution cancel. And that gives us grams of HNO3. So I get 81.83 grams of HNO3. Now, we're going to need the molar mass of HNO3, aren't we? So hydrogen is 1.01, nitrogen is 14.01, and 3 times oxygen. All right. So let's see, 1.01 and 14.01, and then 48 for the oxygen. So this is 63.02 grams per mole. So to find the moles, we need 63.02. No, let's start with the mass. 81.83 grams of HNO3. And now we want to cancel grams and leave us with moles. Right? Grams. So this is 63.02. Divided into 81.83. And that's 1.30. Rounded off to 3 places? Yeah, because that's only 3. Okay, there it is. Oh, excuse me. Wait a minute. Not grams. Silly. Moles. Go ahead. We cancel the grams. Leave us with moles. 17. Let's see here. All right. 17. Determine the normality of a base of 93 milliliters. Normality of a base if 93 milliliters of 1.8 molar HCl is required to neutralize 52 milliliters. Normality. Remember normality. Normality is equivalence per liter. So that could be moles of hydrogen ions or moles of hydroxyl ions. If we're titrating them, and if we know how many moles of hydrogen ions were required, 93 milliliters of 1.8 molar hydrochloric acid, then that equates to the number of moles of hydroxide, or the equivalence of hydroxide. So what we need is, what's the normality of the hydrochloric acid? Right? Hydrochloric acid, 1.8 molar HCl is equal to 1.8 normal HCl. All right. And the volume, this is the normality of HCl, and the volume of HCl is equal to 93 milliliters. Okay. The normality of the base is the question, and required to neutralize 52 milliliters of this solution. So the volume of sodium hydroxide is 52 milliliters. Right? When you know normality, you can use this formula. The normality of the acid times the volume of the acid equals the normality of the base times the volume of the base. Right? Our unknown is the normality of the base here. So the normality of the sodium hydroxide is equal to the normality of HCl times the volume of HCl divided by the volume of sodium hydroxide. Right? So the normality of HCl we determined is 1.8. The volume is 93 milliliters. And the volume of the base is 52.0 milliliters. So the normality of sodium hydroxide is simply that calculation. Let's see. Two significant figures. 3.2 normal. Okay. Now, it just so happens sodium hydroxide only has one hydroxyl. So its normality is also equal to its molarity. All right. Move down to 18. There you go. All right, magnesium metal reacts with hydrochloric acid to form magnesium chloride and hydrogen gas. All right, if we're going to need that formula or that reaction, then we want to say magnesium metal plus hydrochloric acid yields magnesium chloride in solution plus hydrogen gas. Okay? We might as well go ahead and balance it. Magnesiums are okay. Hydrogen, we need 2 hydrogens here. And that gives us 2 chlorides. So we're good. Okay, suppose we react an excess of magnesium metal. Excess. With 19.8 milliliters of 3 molar hydrochloric acid solution. 3 molar, 19.8 mils, yep, 19.8 milliliters. And collect all the hydrogen in a balloon at 25 degrees in 1 atmosphere. So we're given the temperature equals 25 degrees C, and pressure is 1 atmosphere. Okay. What's the volume of the balloon? All right. How can we get volume from those values? Well, we're missing one. Remember? PV equals nRT. Wait a minute. I don't think we've done gases yet. No. Scratch this problem. We haven't covered gases yet, so we can't do the calculation. I mean, I could show you, but it wouldn't mean anything because we haven't studied the nature of gases. All right, so I don't know how that one got in there. Let's throw that one out. Well, I do know how this one got in here. Gases are chapter 13. We haven't done that. We're doing 15 first, and then we'll go back to 13. So forget that one. We'll do one like it when we get to gases. I ought to edit this and cross that one out. Like that. Yep. That one's getting ahead of ourselves here. Let's go to 22. Which of the following solutions contains the smallest number of ions? All right. I'm thinking Henry Ford here, assembly line. If we want to know the smallest number of ions of these solutions, we've got to do the same calculation at least 4 times. So we want to know, first of all, how many moles of the compound, and then relate the moles of the compound to the moles of ions. All right, so we have, if we have molarity times volume equals moles of the compound. So for sodium sulfate, like that, let's go ahead and put the formulas up here. Lithium nitrate. Potassium hydroxide. And iron 3 chloride. There we go. Now the calculations are going to be volume times molarity yields moles. So we have 1 molar, 1, 1, 2, and 2. 1, 1, 2, and 2 molar. If we're just comparing numbers, we don't have to convert milliliters to liters. You can if you want to, but if we multiply molarity times milliliters, we get millimoles. I 39.8. 3056. Okay. That gives us millimoles of compound. What we want is ions. So what's the ratio here? This is compound. So the ratio is for every one of these, we have 3 ions. Or 1 millimole, actually. 3 millimoles of ions. The ratio here is 2 to 1. Ratio there is also 2 to 1. Ratio there is 4 to 1. All right. Now we can do our calculations. Now, in case you don't believe me that millimoles is molarity times milliliters, let's work it backwards. Say we have so many millimoles, and we dissolve it in so many milliliters of solution, right? So why milliliters? What's that going to be equal to? Well, milli cancels milli, and we have moles per liter. There you go. There's your proof. This is 740. That's close enough to determine the winner. Let's see. And this is 1, 2, 2, 2. And this is 189.6 times and then 4 times. This is 1517. So A has the smallest number. At least 2 are not equal. This is the smallest number of ions in that sample. All right, number 25. Assume that vinegar is 0.852 molar solution of acetic acid. That's pretty close. I've seen higher and seen lower. What volume of 0.2136 molar sodium hydroxide would be needed to complete neutralization of 6.89 milliliters? All right, we need the equation. Well, actually, we can do it one of 2 ways. We can do it stoichiometrically with an equation, a reaction equation, and that's useful. So we'll do that one first. So you've got acetic acid aqueous plus sodium hydroxide, and that's equal to sodium C2H3O2 plus water. Okay. Now it appears to be balanced. Yeah, one hydrogen and one hydroxyl makes one water, and then one sodium and one acetate makes the salt. Okay, so that's balanced. What we're given is 0.852 molar. 0.852 molar. And 6.89 milliliters. Okay, we're given the concentration of sodium hydroxide. We're looking for the volume, 0.2136 molar. We're looking for the volume. So if we work it out just like we normally do, we can calculate millimoles here, and that would be equal to millimoles here, whatever that value is. Let's see, 5.8703 millimoles, which is also equal to 5.8703 millimoles. Okay. And since this times this is that, molarity times volume equals moles, and we want to find volume equals that divided by molarity. All right, so 5.8703 millimoles divided by 0.2136 molar. And this is 27.5 milliliters. Okay. The other way we could have worked it would be normality of the acid times volume of acid equals normality of the base times the volume of the base. And since these are one proton, one hydroxyl, then the molarity and the normality are equal. And you get exactly the same answer like we did before in a previous problem. Let's see, 26. For the reaction between 200 milliliters of 0.1 molar silver nitrate and 95 milliliters of 0.1 molar sodium chloride, concentration of silver ions in solution after the reaction is complete is 0.1, less than 0.1, greater than 0.1, and some other factors. So we've got that same reaction that we looked at earlier. Silver nitrate? Yes, silver nitrate. That yields silver chloride solid plus sodium nitrate. Okay, what are we given? 200 milliliters of 0.1 molar silver nitrate. 0.1 molar, 200 milliliters. And 0.1 molar sodium chloride, same concentration. And this is 95 milliliters. All right. So since we have the same concentration, in order to be stoichiometric, we would need equal amounts in volume. Since we don't have equal amounts, then the smaller volume is limiting. This one's going to run out first because it's less than that one. And this is excess. Okay. Concentration of silver ions. Since this is excess, we will have extra ions. So let's see, how many ions would this produce? It'd be 20 millimole of silver ions because they're 1-to-1. This would be 9.50 millimoles of chloride. Yeah, or sodium chloride, which means that we would be using up that much, 9.50 millimoles of silver required. Okay, so if we subtract that from this one, 5 and 9 from 19 is 10 millimoles of silver remain. Okay, so if we're talking about concentration here, this is how much is left over. What's the total volume? 295 milliliters. Right? Milliliters. Remember, millimoles divided by milliliters is molarity. So this is, this is 3.56 times 10 to the minus 2 molar silver ions. After the reaction is complete, concentration of silver is 0.1. No, it's less than 0.1. Yes. C also says greater than 0.1, so we can throw A and C out. A, B, C, and D. Those are not possible. B says less. So this is, B is possible. D says less. It's also possible. E says 0. All the silver ions are used up. No, that's false. We do have excess silver. We proved that already. So between B and D, so what's the difference? B says less than 0.1. Some but not all of the silver ions are used to make the precipitate. That's true. Yeah, that is definitely true. How about D? Even though silver ions do not react, they are diluted. Silver ions do react. So there's our answer right there. B. $29. Did we do one like this before? No, this is different. All right, 29. Okay, what do we got? Nitric acid solution containing 71% HNO3 by mass. Has a density of 1.42 grams per mil. Okay, so we're given the concentration in mass percent. So the concentration of HNO3 is 71.0% mass. We're also given the density of the solution at 1.42 grams per mil. Okay. How many moles of HNO3 are present in 2.36 liters of this solution? So the volume of the solution is 2.36 liters. All right. And the question is, how many moles of HNO3? There we go. That's everything we know and the question. So how do we get there? Well, if we need to know moles, we got to know grams so that we can use molar mass to convert. So how do you get grams? Well, we know liters and density, so we can find out how many grams of solution. Then we can convert from grams of solution to grams of HNO3, and we're off to the races. So we need compatible units here. 2.36 liters is 2360 milliliters, right? The unit gets smaller, the number gets bigger, 3 places, right? So if we multiply that times 1.42 grams per milliliter, we will get the mass of the solution. (3.351 times 10 to the third grams). Now we can convert that using this relationship. So we have 3.351 times 10 to the third grams of solution. And this is for every 100 grams of solution, we have 71.0 grams of HNO3. That's what that means. And I get 2.379 times 10 to the third grams of HNO3. Now we can convert that to moles. And that's what we want. We want moles. All right, so what's the molar mass of HNO3? Well, I erased it, so we have to calculate it again. Hydrogen, nitrogen, oxygen. This is 63.02 grams per mole. Divided into that value. And let's see, standard notation. All right, rounded off to 3 places, I believe. Yeah, 3 places. So that's move the decimal, 37.8 moles of HNO3. There you go. Think way back to the beginning of the semester when we were talking about conversion factors. I said a large number of chemistry problems can be solved by dimensional analysis. Just watch your units. That's what we've done here. Of course, we have to understand the chemistry, but the mathematics is simply unit conversion. And if you track your units, keep yourself honest with units, then you can't go wrong. Did we already do this one? Well, 2 solutions of sodium chloride. Oh, no. This is a new one. All right. This is new. All right. 38. 2 solutions of sodium chloride. One is 2 molar and the other is 5 molar. So we have solution 1 is 2 molar solution 2 is 5 molar. Okay. You have much more 5 molar solution, and you add the solutions together. Which of the following would be the concentration of the final solution? You have much more. Oh, okay. We say which could be the concentration. It doesn't say that it actually is, but let's see. If we have this volume is much greater than this volume, right? What would happen if they were equal volumes? If they were equal volumes and you put them together, then the concentration would be halfway in between, right? If V1 equals V2, then the mixture concentration would be 2 plus 5 divided by 2, which would be 3.5. Right? But since we have more of this, concentration is going to be shifted closer to 5. All right, let's look at our options. Look at the answers. See which ones are reasonable. The first one is 7.2. Can you get a higher concentration by putting these two together? No, you can't. It has to be less than the highest one. So this one is false. 3.5, we did that one already. That's if the volumes are equal, and they're not. Okay? How about 2, 9, 4, 8, and 7? 2, 9, 4, 8, and 7. This one is like that one. You can't get something for nothing. So it's toss up between these two. So if this one is a greater volume, then the mixture is going to be greater than 3.5 because this is the midpoint. So it has to be more than 3.5. That means this one cannot be either. It's too little. So this is the only reasonable conclusion, 4.8 out of those that were given. Okay, we did that one already. Go down to 50. Okay, what's the normality of 1 liter sodium hydroxide solution that contains 18.2 grams of sodium hydroxide? All right, so we have mass of sodium hydroxide is 18.2 grams. And the volume is 1 liter. We got to know the moles. Once we find the moles, that's going to be not just the moles of sodium hydroxide, it's also the moles of hydroxide ions. So let's convert this to moles, right? Sodium hydroxide. Sodium is 23 to 2 decimal places, oxygen and hydrogen. Grams per mole. So take 18.2 divided by 40.01, and that's 0.4549 moles of sodium hydroxide. Okay, that's also 0.4549 moles of hydroxide ions, which is that many equivalents. right? So the normality then is 0.4549 equivalents divided by 1 liter equals 0.455 normal. Okay? Next, 52. Okay, let's see. You have 3 liters of 3.77 molar sodium chloride, 2 liters of 2 molar silver nitrate. Mix them together. What's the concentration of chloride ion in solution? Did we do this one already? We did one like it, I think. So we should be able to knock this one out pretty quick. Back to this equation. Sodium chloride plus silver nitrate yields silver chloride solid plus sodium nitrate aqueous. Okay. Starting with solution A, 3 liters of 3.77 molar. Okay. And silver nitrate is solution B, 2 and 2. All right. So, and the question is concentration of chloride ions. So we want to know chloride ion concentration. All right. We need to find the limiting one. 3.77 times 3 is 11.31 moles of sodium chloride. And this is 4 moles of silver nitrate. Okay, I think we can tell which one's limiting because it's 1 to 1. This would make that much silver chloride. This would make that much. This makes the least amount. This is limiting. This is excess. Oops. Let's try that again. Okay, if we're going to find the chloride ion concentration, we didn't use up all the chloride ions. There's some left over, right? Because this is excess. So how many chloride ions did we use? Well, we would make 4 moles of silver chloride, which is 4 moles of chloride ions used. And we have 11.31 moles of chloride to start. So we just subtract the 2, right? 11.31 minus 4 is 7.31 moles of chloride remain. Now all we have to do is divide moles by liters, and we get our concentration. So how many liters? 3 plus 2 is 5. And that's 1.46 molar chloride ions in solution. All right, that was pretty quick. Okay. What have we here? Phenol. Yeah. HC6H50 is phenol. Everybody knows phenol, right? Chloroseptic. Spray your throat with chloroseptic. you're spraying phenol into your throat. It deadens the nerves and gives you some relief from that sore throat. It's not a strong acid, not particularly toxic. Okay, 1.61 grams, let's see, 55. 1.61 grams of solid acid, HC6H5O. Let's see, mass of HC6H5O. Mass is 1.61 grams. Okay, given that, neutralized 11.61 milliliters of sodium hydroxide. So the volume of sodium hydroxide that was neutralized is 11.61 milliliters. Okay. And we're given the reaction. What's the molarity of the base solution? All right. Well, this is a single proton, and this is a single hydroxyl, right? So we can say, we can either do it this way. We can do normality of the acid times volume of the acid, normality of the base times volume of the base. Okay, we need to know the number of moles here. So what we need is molar mass. All right, so we have 6 hydrogens. Let's see, let's do it over here. 6 hydrogens and 6 carbons and 1 oxygen. Do a quick calculation here. And 16. This is 9412 grams per mole. 94.12 divided into 1.61 is 1.7106 times 10 to the minus 2 moles of this acid. Okay. Let's see. All right. Here's the assumption we have to make. If we have 1.61 grams of that acid and we add 11.61 milliliters of sodium hydroxide solution to neutralize it, the final volume we must assume is 11.61 milliliters, right? It may not be, but the problem limits us to that value. So the volume of the final solution is that, right? All right. You know what? We don't need this. We've got moles of acid, right? This is moles of acid. And because 1 proton, 1 hydroxyl, this is also moles of base. Divided by, we have to change that to liters. Times 10 to the minus 3 liters. Right? I just changed that milli to 10 to the minus 3, just like before. So 11.61 So I get 1.47 molar. Okay? That's it. That's all she wrote. Oh, got another one. Okay, 59. All right, what volume of 0.176 molar sodium sulfide solution contains 1.01 grams of sodium ions? All right, so what are we given? 0.176 molar sodium sulfide. So molarity of sodium sulfide equals 176. 76 molar. And we want to end up with 1.01 grams of sodium ions. So the mass of sodium ions equals 1.01. Okay. Now, since electrons don't weigh much at all, we can assume that the molar mass of sodium ions is the same as the molar mass of sodium atoms. Otherwise, we're stuck. So, how many moles of sodium ions are required to solve this problem? Right? It should be what, 23? Yeah, 23 grams per mole sodium. So it's 1.01 and 23 divide is 4.391 times 10 to the minus 2 moles of sodium ions. Okay. The question, let's go back to the question, what volume? We want to know the volume of sodium sulfide solution, right? So molarity is equal to moles per volume solution. Okay. We got moles of sodium. We just need to convert to moles of sodium sulfide. So if this is the moles of sodium ions, what's the relationship? Sodium ions per sodium sulfide. It's 2 to 1. 2 of these for every one of those. So if we divide that by 2, we get this many moles of sodium sulfide. 196 times 10 to the minus 2 moles and volume. So in order to get volume, bring volume over here, bring that value over here. We're going to divide this one by that one. And let's see, our units are in liters. Okay. So volume equals, I'll go ahead and put it in here like this. 2.196 times 10 to the minus 2 moles divided by 0.176 moles per liter. And that's equal to 0.125 liters. Okay. $62. Yeah, I'm running out of time. How many more do I got? 62, 1, 2, 3, 4. 4 more. Yeah, I might run over a little bit, but I'd rather do that than break it up. 62. $62. 15 milliliters of 0.3 molar sodium phosphate reacts with 20 milliliters of lead-2 nitrate solution. What's the concentration of phosphate ions left in solution after the reaction? All right. Let's put what we got up here. We got a reaction here between sodium phosphate This is the 3 minus, this is a +1, so this needs to be 3. This is in solution, and we're reacting it with lead 2 nitrate. Lead 2 nitrate. So we need 2 of these in aqueous solution. So what do we get? Lead reacts with a phosphate. Phosphate. So how do you balance that one? Cross multiply. Bring the 3 over here and the 2 over there. And you look it up in your solubility chart and find that it's insoluble. And what's left over? What's left over is sodium nitrate. Okay. Now we need to balance. Usually these things balance pretty easy. Let me see if I can figure this one out. If we got 2 phosphates there, we need 2 here. And we need 3 leads. So that would give us 3 leads. That would give us 6 nitrates. So if I put a 2 here, that gives us 6 nitrates, 2 phosphates, 3 leads, and 6, let's see. 6, there we go. 6 sodiums and 6 nitrates. We're good. Now, if you want to, you can use the budget method, that's fine. But we have a balanced equation now, we can put in the values. 0.3 molar of this compound, and we have 15 milliliters. And the lead 2 nitrate is 0.2 and 20. Okay. We got to find out which one's limiting if we're going to answer concentration of phosphate. So how much of this is left over? Well, we got to prove that that's excess first. So how many millimoles do we have here? 0.3 times 15 is 4.5 millimoles of sodium phosphate. This one is 4, right? 0.2 and 20. Yeah, 4. So I'm going to put this one down here. 4 millimoles of lead 2 nitrate. Okay. So we got to convert this to our precipitate. All right, the ratio is from the coefficients of the balanced equation. All right, that's 1, and this is 2. So this 2 will cancel. There, 1. So that's 1/2. 2.25, right? Yeah. This is 2.25 moles of lead 2 phosphate. Okay. This one, by a similar procedure, and let's see, lead 2 nitrate is 3 to 1. So we divide this one by 3. 1.33. Okay, so we know which one's limiting. I mean, which one, yes, which one is limiting? This one. And this one is excess. All right. So, if the question is concentration of phosphate, how much phosphate did we use to make that compound? If it's 1.33 moles of lead 2 phosphate, for every one of these, we needed 2 phosphates. So times 2 equals 2.67 actually, because this is 3. Moles. No, millimoles, excuse me. Millimoles. 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 There. And how many did we start with? Well, we started with 4.5 millimoles of this compound, but there's 1 phosphate for every one of these. That means we started with 4.5 millimoles of phosphate start, and we used 2.67 millimoles of phosphate. We subtract them, and I get 1.83 millimoles of phosphate remain. Now we just need to divide that by milliliters. Millimoles divided by milliliters. We had 15 plus 20, which is 35 milliliters. And that gives us 5.24 times 10 to the minus 2 molar. Oh, standard notation. Move it 2 to the left. 0.052 molar. There you go. This is phosphate in aqueous solution remaining after the reaction takes place. All right. Next, 64. Ooh, that's getting kind of light. Let's try this one. When a solvent has dissolved all of the solute that it can at a particular temperature, it's said to be saturated. That's just definition. Okay. 65. If you mix 20 milliliters of 3 molar sugar solution with 30 milliliters of 557, you will end up with a sugar solution of. All right. So what we need is how many moles of sugar are we starting with, and what's the final volume? Right. So if we are starting with 20 milliliters of 3 molar, 20 milliliters of 3 molar, that gives us moles of sugar in the first solution. 30 milliliters of 5.57. Right? That gives us total millimoles of sugar. Now what's the volume? Well, 20 plus 30, right? That's the final volume. And that'll give us molarity. This is millimoles plus millimoles divided by milliliters. And I get 0.71. 1 molar. Oops. Okay, what did I do wrong? You will end up with a sugar solution of 4.54 molar. Well, that's more reasonable. I made a miscalculation here. 20 times 3, 30 times 557. Hold on a second. Let's do that again. 20 times 3, okay? And then 30 times 5.57 plus, so that's 227 millimoles. Yeah, my mistake. 50. This is 4.54 molar. That's a case where you check yourself at the end to see if it makes sense. I didn't do that. I should have said, whoa, less than 1? We started out with 3 molar and 5.57 molar. Can't be less than 1. And I think, what, one more? 74. Go over just a little bit. "15 milliliters of 0.3 molar phosphate solution react with 20 milliliters of 0.3 molar nitrate solution. What's the concentration of nitrate ions left in solution after the reaction is complete?" Okay. What are the nitrates doing? Nothing. Nitrates, the only purpose for the nitrates is to get that lead into solution. The nitrate is a spectator. So all we need to calculate is the total moles of nitrate divided by the total volume. So the nitrate comes from 20 milliliters of 0.3 molar. 20 milliliters of 0.3, right? Molar. Lead 2 nitrate. That's 6 millimoles of lead 2 nitrate, right? Yes, 2. Okay. How many millimoles of nitrate? Well, for every one of these, you got 2 of those. So we have twice as many nitrate ions. 12 millimoles of nitrate. Then we want to divide by the total volume, which is what? 20 plus 15 is 35 milliliters. And that's 0.343 molar nitrate. Okay. Let's see. I think that's it. Yep. We're done for today. So this is Thursday. Next Tuesday will be a tutorial session. So I'll just zoom in from my office and I'll put a note on the door in case anybody shows up. And you just come down to my office and we'll hash it out, or you can zoom in and we'll talk about it. Otherwise, this exam will be by midnight in Brightspace by midnight a week from today, Thursday.